Colligative properties refers to the fact that when we make a solution, the properties of our solution are different from the properties of our pure solvent. What ends up happening is the vapor pressure goes down, the boiling point goes up, the freezing point goes down, and we have something called osmotic pressure. So we can take a look at all of these different properties and try to put them into an understanding of what's happening with our solutions. All right, so if I look at a phase diagram, I have my different regions. My blue line is my pure solvent, and my red line is what happens with the solution. And so you can see that our melting point goes down and our boiling point goes up. All right. If I look at water, so this is the phase diagram for water, right? The freezing point will go down and the boiling point will go up. All right, so we know we've got a 0 degrees Celsius freezing point, and we have 100 degrees Celsius boiling point of water when it's pure. And so our freezing point goes down. So our delta TF is going to be less than 0 degrees. And our delta TB is going to be greater than 100 degrees. So we calculate the change, and then we add to or subtract from our pure. Okay, but let's take a look at our vapor pressure. So here I have two diagrams. All right, I've got a pure solvent. So in my pure solvent, I have solvent molecules. And in my solution, I have non-volatile solute molecules. Okay, keeping in mind this non-volatile. Non-volatile means something that doesn't evaporate. So like sodium chloride, that's non-volatile. Now if I mix like water and ethanol, ethanol is volatile, and that has a slightly different consideration because then I have two things competing for the vapor phase. But when I'm looking at a solvent with a non-volatile solute, all right, that non-volatile solute doesn't enter the vapor phase. And what we get is the vapor pressure of a solution is always lower than the vapor pressure of the corresponding pure solvent. Okay, those non-volatile solute particles or even volatile solute particles get in the way, and it prevents more particles from reaching the vapor phase. And so the vapor pressure goes down. Fewer molecules in the vapor phase, less pressure. So vapor phase goes down. So we have this thing called Raoult's law. Raoult's law lets us relate the pressure to the mole fraction, all right? Where the pressure of the solvent without that naught symbol is the vapor pressure of a solvent above a solution, okay? X solvent is the mole fraction of the solvent. And this P naught is the vapor pressure of the pure solvent. Okay? We can also look at the pressure by understanding the change in the pressure. So the change in the pressure is just, you know, the pure minus the solvent or the solution. That gives us our delta P. And this one's interesting. Instead of being the solvent mole fraction times the pure vapor pressure of the solvent, it's the solute mole fraction times the vapor pressure of the pure solvent. Okay? All right, so let's take a look. All right, so we want to know what the vapor pressure of a solution made of 10 grams of glucose and 100 grams of water at 37 degrees Celsius is. From our CRC, we can look up that the vapor pressure of water is 37 degrees Celsius at 47.1 torr. All right, so we can look at this two different ways. We can look at this just a straight calculation, or maybe we're given a piece of information. Maybe they only give us the mole fraction of the solute. Maybe we're not given all the information. Well, how could we get the vapor pressure of our solution from that way? So let's take a look at both ways. Okay, all right, so we are going to need to know the moles of our glucose and our water for both methods. So let's do our mole calculations. 10 grams of glucose times 1 mole and 180.156 grams gives us 0.0555 moles of glucose. And I have 100 grams of water. 1 mole and 18.016 grams gives me 5.55 moles. I know, the numbers are crazy because those molar masses, 180 versus 18, we get numerically the same, but orders of magnitude different. Okay, all right, so methodology 1, we're going to do our this is easy, it's nice and direct. For this one, we need the mole fraction of our solvent. So the mole fraction of our water, we get 5.55 over 0.0555 plus 5.55. We get a very high mole fraction. There's not a whole lot of glucose in the solution. Very, very high. Okay, so the pressure of our water is going to be 0.99. Remember, mole fraction is unitless. And that's times 47.1 torr. And so we get 46.6 torr. Okay? But again, let's say you're given the mole fraction of the solvent. Can you figure out what the new vapor pressure is? Absolutely. Oh, I thought I had another slide. We'll just do it on this slide. We get our X of glucose. This one was my fault, not my technology. I thought I put an extra slide in there. Point that 0.0555 over 0.0555 plus 5.55. We get 0.00990. So our delta P, 0.00990 times our 47.1 torr gives us 0.466 torr. So the pressure is 47.1 torr minus 0.466 torr, which gives us the same 46.6 torr. Okay, there we go, we're good. All right, so why does this happen? So remember, we have our thermodynamic relationship, okay? So when I look at this, what is the same for the solvent and the solution? Okay. Our delta H of vaporization is the same, minus this T delta S. And this is smaller for the solution. Okay, that T delta S term goes down. Why? Well, because it's delta S of vaporization. If I have fewer molecules in the vapor phase, I have less disorder. Okay. And so that means delta G is less negative. And so that vapor pressure goes down. Okay. Now, when I look at two volatile solvents or two volatile substances like benzene and toluene, I have to look at the vapor pressures of both because they both vaporize. And so the vapor pressure of my solution is going to be a mixture of both vapor pressures, all right? And so this is 2 Okay, they both vaporize. Okay. Okay, two volatile substances, they both vaporize. Now, at a certain crossover point of their mole fractions, they'll converge on each other. But if I start with all benzene and no toluene, the vapor pressure is going to be the vapor pressure of benzene. As I get rid of benzene and I have more toluene, then my vapor pressure is going to be just the vapor pressure of the toluene and not the benzene. But as long as they're mixed, I'm going to get a combination of both because they're both in the vapor phase. Now, obviously, we see deviations from this. The ideal solution, all right, is what we get over there in A. But let's say I have strong interactions between my solute and my solvent. It makes it harder even still for stuff to go into the vapor phase. And so I see a deviation there. It lowers, all right? When I get the maximum mix of the two of them, they hold each other strongly. And so my vapor pressure gets even further down. But if I have weak interactions, then maybe the two components don't stick together as well as just the individual components. And so they vaporize even easier. And so the vapor pressure of my solution can be elevated. All right. And so we can see these deviations as we go through. Okay. Now, when we look at this, we also change our boiling and our freezing points. Okay. So we get this equation here, this delta T is equal to this K sub B times the molality. So the delta T is the boiling point elevation, so the change in boiling point, and it's boiling point elevation, so it goes up. This is a constant. And each solvent has a unique Kb, and then M is the molality. Okay. We get something similar, but it's freezing point depression, and so my delta T, this is the change in freezing point. Okay, and it goes down. And then K sub F, a constant. Like K sub B, every has a unique. And you don't have to memorize K sub B or K sub F. I will always give these to you if you need them, either on an equation sheet or in the problem itself. And then M is still the molality. Okay? All right, so when we look at these, our boiling point. So what happens here? Why does the boiling point go up? Well, that entropy of the boiling is decreased. And so we need a higher temperature to bring delta G to 0. All right, so we have less disorder. Same thing with the vapor pressure. Okay, so higher temperature to get to the boiling point because we have less disorder there. And so not as many molecules are reaching the vapor phase at the same normal temperature. So we have to go higher temperature to get those to reach the vapor phase. What we get is we get solute molecules that take up the surface positions of the liquid. And so fewer molecules can evaporate, more energy is required to vaporize them. For freezing, all right, the entropy is increased because now I have all this extra stuff there. And so when I freeze, my crystal lattice is not nearly as organized as it normally is because I have all these extra stuff things, peppered throughout. And so the temperature required to get delta G to 0 is reduced. And so we get that interference of our solute molecules They make it so the crystal formation is harder to do, and so we get a lower temperature. We have to get even colder to cause that crystallization to occur. Okay, so let's try a problem. Okay, so I've got a solution of water and ethylene glycol. Ethylene glycol is common antifreeze. All right, so if you live someplace where it freezes, you put ethylene glycol antifreeze into your car's radiator to prevent your radiator block from freezing and thus cracking, because water expands as it freezes. And so if your radiator, if all the water in it freezes, it expands and it can cause your radiator block to crack. Bad news, car won't work. All right, and so what is the new freezing point and new boiling point of this particular solution with 100 grams of ethylene glycol for 90 grams of water? All right, and so our molar mass of ethylene glycol is 62.068 grams per mole. For both of these, we have to use the molality. It's the same solution, so we need one molality. So let's calculate the molality. So I need my moles of ethylene glycol. So I have 100 grams times 1 mole in 62.068 grams. So I get 1.611 moles. And so my molality, remember, is the moles of the solute over kilograms of solvent. So I get 1.611 over 0.900 kilograms. So I get a solution that's 1.79 molal. All right. So now let's take a look at our new boiling and freezing points. All right. So our change in boiling point is going to be that Kb, the 0.52 degrees Celsius per molality, times my 1.79 molal. So I get 0.931 degrees Celsius. So what that says is that my boiling point changes by 0.931. So the boiling point goes up. So what we do is we take the original boiling point, 100 degrees Celsius plus 0.931 degrees Celsius equals 100.931 degrees Celsius. Okay, because water boils at 100 degrees Celsius normally. So now we're going to go up. So we add them. Okay, my freezing point, 1.86 degrees Celsius per molality, same solution, so still 1.79 molal. We get 3.33 degrees Celsius. So now remember it's freezing point depression. So we're going to take our original freezing point of water and subtract from it our new freezing point. So we get negative 3.33 degrees Celsius. Okay. All right. Now we can use this information to help us figure out a molar mass or a molecular formula. So, all right. So I've got this tartaric acid. Okay. We can get our tartaric acid from crystalline residues found in wine vats. We use it in baking powders, we use it in food. All right, so we have 32.3% carbon, 3.97% hydrogen, and then the rest is oxygen. So if I have some tartaric acid dissolved in water, the solution freezes at negative 1.26 degrees Celsius. Okay, which means my delta T sub F is 1.26 degrees Celsius because the regular freezing point of water is what? 0. So my change in freezing point was 1.26 degrees Celsius. Okay. All right, so now let's take a look here. So we need to figure out two pieces of information. We need to figure out the empirical and molecular formulas. So the empirical formula we've done a zillion times before. All right, we're just going to do our percent composition. So I have 32.3%, so it's 32.3 grams of carbon times 1 mole and 12.01 grams gives me 2.689. Hydrogen was 3.97. 1 mole, 1.008 grams, 3.938. Oxygen was the rest, so I do 100% minus 32.3% minus 3.97% gives me 63.73%. Okay, percent composition out of 100 grams makes that 63.73 grams of oxygen, 1 mole, 16 grams gives me 3.983 moles of oxygen. All right, so I get carbon 2.689, hydrogen, whoa, that jumped way ahead. Okay, well, we're gonna have to finish solving on here because I can't go back, and I really don't feel like re-recording this whole presentation because it is jumping on me. So I do think that my screen sensitivity is going down. Anyway, so you've done percent composition before. So you should get C2H3O3 as the empirical formula. And the molar mass of the empirical formula should be 75.044 grams per mole. Okay, so we knew that our change in freezing point was 1.26. All right, so we can do 1.26 is equal to 1.86 degrees Celsius per molality, because we're still dealing with water, times the molality. We get a molality that is equal to 0.677. All right, so I can get 0.01123 kilograms of water times 0.677 moles of my tartaric acid for every 1 kilogram of water. Gives me 7.607 times 10 to the negative third moles of my tartaric acid. And then the molar mass, we get 1.161 grams over our 7.607 times 10 to the negative third. So we get 152.6 grams per mole. And we get a molecular formula of C4H6O6. Okay, so you can use the empirical formula, and then you can use this data to figure out the molality. And from the molality, you get moles. And if you have grams of your original sample, you can get your molar mass. And then the rest is a problem like you've solved before. We've done empirical molecular formulas. All right? Okay, now osmotic pressure. I apologize. I need to see what is going on with my iPad because there's no reason why in the middle of writing it should advance 2 slides randomly. So I think there's something wrong with the touch screen because this iPad I've had for, gosh, I got this before COVID. So this iPad is over 5 years old. Yeah, so the touch screen is probably starting to go. All right. Now our last colligative property is osmotic pressure. So I get this capital pi is equal to capital M RT. All right, and so you can see their derivation over there where we're looking at moles over volume times RT. Well, moles over volume gives us molarity. All right, and so that's all derived off of our ideal gas law. All right, so our capital pi is our osmotic pressure. Okay, capital M, this time it's molarity. R is the gas constant, usually the 0.08206 liter atmosphere, mole Kelvin, because we're not dealing in energy this time, so we're back to this one. And then T is temp in Kelvin. Okay? All right, so when we look at osmotic pressure, all right, I've got this semi-permeable membrane. I have a solution, I have a pure solvent, okay? And so we have a concentration gradient difference. And so, because my solute particles can't get through that semipermeable membrane, and so they flow. All right, they flow between to equalize that pressure. All right, so initially I've got my solvent and my solute. I've got my water, and so it's going to move from one side or the other to equalize that pressure. And so over here, we've got this, difference here. All right, so the pressure of excess fluid is equal to the osmotic pressure of the solution. Okay? Potentially, you may have dealt with dialysis tubing in another class or maybe a biology course. And so if you stick, like a saline solution into your dialysis tubing and you've got something like this, over time, the water level will rise because more of your solvent, if it's water, or whatever your solvent is, more will flow into there and cause the solution volume to rise. And so the change there is that osmotic pressure. All right, osmotic pressure is important in our bodies because we have an electrolyte balance that has to happen. And so if we're isoosmotic, we've got our nice normal red blood cell. Hyperosmotic, it's all shriveled up because it's flowing out of the red blood cell. And then we get a swollen blood cell for this hypoosmotic solution because everything's flowing into the red blood cell. Both of these are bad. If too much flows in, it can cause the blood cells to burst, and then they get stuck in places where they're not supposed to go. The hyperosmotic is all shriveled. It also will get stuck, and so these can cause buildups of plaque and stuff in your bodies and cause clots and clogs. All right. This right here is a diagram of desalinization, where the idea is to force pressure into, so you bring seawater in, you force pressure in, so you push down on that, and so you force the pure water to go through the semipermeable membrane, and therefore you desalinate the water, and now you have potable, potentially, probably more purification needs, but the goal is to have potable water instead of undrinkable seawater. Okay? All right, so let's try an example. This is similar to the example that spazzed out on me, where we're going to use some colligative property data to try to figure out the moles of something and then its molar mass. Now, pepsin is a macromolecule. These are huge. So we're going to get a giant molar mass here. So I've got 3 grams of pepsin, 10 mils of solution. I've got an osmotic pressure. What's my molecular mass? Okay. All right. So we've got our osmotic pressure is equal to mRT. And so we're going to solve this for that molarity. All right, our temperature, we had 25 degrees Celsius. We need Kelvin, so 298.15 Kelvin. Okay, so we had an osmotic pressure of 0.213 atmospheres. We don't know our molarity. We're going to use the 0.08206 liter atmosphere, mole Kelvin, and our temperature was 298.15 Kelvin. So when we solve, we get a molarity of 0.008. Now remember, this is moles of pepsin per liter. Okay. All right. Well, molar mass is grams per mole, so I need moles. So I have 10 mils of solution. I need a liter for every 1,000 milliliters. And then now with that molarity, I have 0.008706 moles of my pepsin for every 1 liter of my solution. And so I get 8.706 times 10 to the negative 5th moles of pepsin. Okay. For my problem, I have grams, which that was 3.00 grams. Now I have moles, 8.706. It's 10 negative fifth moles. And again, macromolecule, it's huge, all right? 34,459.4 grams per mole. All right, so we can use this colligative property data to help us figure out information like a molar mass. All right, there's one other thing we have to consider with colligative properties, and that's the Van Hoff factor. All right, and we're going to talk about that in the next video. The Van Hoff factor takes into consideration that not everything is like glucose or ethylene glycol, where it is a molecular compound, not ionic. What happens with an ionic substance, where something like sodium chloride, when it dissolves, I don't just have individual sodium chlorides. My one sodium chloride formula unit gives me 2 particles. So what happens then? That's what we'll consider to wrap this up.